All right.
Okay. Is this visible?
Yes.
Okay, perfect. Well, I'm happy to start whenever you want me to. If you want to wait a few minutes, that's fine with me.
Irene, what's your take? Can we start?
Sorry.
Do you want to say something? You said you wanted 30 seconds.
I
Maybe
do. So just very briefly, NASA ULI is willing to fund one intern for the summer. So if you have anybody who would be interested in spending the summer at NASA Langley, working something that's going to be pertinent to the ULI, which is a pretty broad brush, the person has to be a U.S. citizen. That's the one constraint that we have. So please send me an email, both with the with the individual and again what your interest would be, and then we'll see how many interests we get, and then how we put that in, and I'll be in touch in terms of how to go about applying, et cetera, et cetera, et cetera. But I think in some respects it's coming up pretty quickly. So if you're interested, please let me know soonest. So thank you.
So Melkior, I think you can get started and we'll see if people join.
Perfect. I'm happy to do it. Okay, so I was thinking about what to talk about today, and I figured that since there's been quite a few people, which was great to see at the 2 or 3 SciTech talks that were related to ULI that my group gave in Orlando, that would give a kind of a more high-level story of what we're doing, and hopefully in some ways complementary to some of the shorter-term activities that we were involved with that were published in SciTech. And so the title of the talk is very it's very wordy, right? Autonomous system resilience and guaranteed performance in the face of unexpected adversity. And so to help unpack some of this, some of these words, I want to share a short video that hopefully it says I'm sharing the sound, so hopefully you can hear the sound. If not, there should be subtitles. It's maybe 2 minutes, and that kind of gives gives an impression or gives an example of the kind of stories that we might be interested in exploring. So I'll go to the next slide and let me know if you can't hear the sound.
6-8 Zulu is declare an emergency. 6-8 Zulu declare an emergency. 6-8 Zulu declare an emergency.
6-8 Zulu, Roger. You want to come in for runway 20?
I don't know if we can get there. 6-8 Zulu.
6-8 Zulu, say again.
I don't know if we can get there. We just lost our engine power. Something's happened.
8 Zulu, Roger. Wind is 230 at 10. You're clear to land any runway at Santa Fe. Altimeter 3020. Can you give me some information?
Okay, I'm 6 about south. I've got a big vibration going on. My prop's going bad here, and I don't know what's going on. And I've been set 8,500. I don't think I can get to the runway.
Make straight in for runway 2 if you can, but the wind is going to be a tailwind, 230 at 10. You can have any runway you want. Clear to land.
I don't know what's happened here. I have no oil pressure.
Right on the final for runway 2. You're 7 miles from the airport.
I don't think I can get. I'm not gonna make it. So, let's see. Where's our best place to go? I'm gonna try to stay away from that ravine. Freeway.
I-25 is in your vicinity, and maybe the frontage road off of I-25. There's 3025.
3025. I'm just not gonna make that. I'm not gonna make it.
We're 6-8 Zulu, and can you tell me what's going on now?
Try to land on the freeway here if I can. My engine. I have lost the engine, and I'll do the best I can here. to try to land on the freeway here or on the frontage road? I think I'll take the frontage road.
That'll be a good idea if you can. The Santa Fe winds are 240 at Niner.
Landed. I'm landed. I'm landed.
Okay, so I included these last few seconds just to kind of make sure to tell you that everything is okay with the pilot. The pilot survived, but this is the story that I'm interested in exploring. So what happened here is we had an airplane. It was a small private airplane, not the one pictured here, where something went wrong, and it is not entirely even clear to the pilot at the beginning what is wrong, and then these errors or these faults kind of seem to be compounding. He kind of says, "Oh, I have a big vibration going on," and he says, "Oh, I lost the engine power," and so there's a lot of uncertainty here about what's going on. And what the pilot is ultimately seeking is what I would call maximal understanding in the face of this kind of minimal or limited knowledge that he has. Now, in itself, this is a classical and very valuable control story. Certainly, the goals of different flavors of robust control or adaptive control are to reach the objective under some lack of knowledge of the dynamics. The problem that we have here, and the problem that the pilot seems to have faced here, or at least believed that he faced here, was that the objective might not be reachable. So if there are no physical capabilities to land, if you can simply not make it, at that point there's kind of limits to what robust control or adaptive control or any other kind of control can do. If there is no control law that will take you to your destination, then you can't do anything. And so in this case, the pilot did what the FAA regulations say that he should do. So he decided on an alternative target, an alternative destination. And in this case, there were no runways around, and so he kind of decided on the freeway or the frontage road of the freeway. And so he says relatively early, okay, let me take the interstate or the frontage road, and then he kind of figures out how to get there, and then in this case he succeeds. And so this is the story that I want to explore. This is a story in which the control is a part of it, but a part of it is deciding on where we can try going. And so in terms of kind of the standard term that people use, pilot in command, that kind of implies that the pilot has the final authority on everything that's happening in the airplane. I want to develop something that I would call autopilot in command. So a system that is not simply oriented towards trying to achieve the task as best as possible, but it has some sort of higher level reasoning of what am I certified, what can I believe to achieve, given that I don't know everything, given that the system changed now. And so formally, what I'm interested in this talk, and what a lot of our, although not all of our activities related to the ULI have kind of been, is try to get some sort of conservative estimates of completable tasks given a change in system, whatever change in the system means. Formally, it means this. I have some sort of a partially known novel transition model that happens after an adverse event. I call it partially known because there is some knowledge that I have. I have the original kind of nominal transition model that helps me in some way. I have some knowledge of the design of the aircraft that also helps me know something about how the aircraft is operating. I have some knowledge of physical laws. So I do have some pretty heterogeneous partial knowledge. I also have a partially or imperfectly observed past trajectory or current trajectory of the system that should also give me some information about what I'm capable of doing or not capable of doing. And so I want to focus on, first of all, this word conservative estimate of completable tasks. So I'm looking for something akin to formal validation. I'm looking for something where I can say, hey, regardless of what the ground truth is, for all possible ground truths that are consistent with the knowledge that I have, I can complete this task. And this happens before figuring out how to complete this task. These are two different topics. How to complete this task comes second and certainly requires some online learning, some adaptation, some robustness. But I want to do this before learning how to complete the task. And perhaps I want to even have a loop here where I figure out, okay, I'm definitely capable of doing this. And then I learn a little bit, and now I become less conservative. And I say, oh, I'm actually capable of doing this as well. And then I kind of proceed and become less conservative. And so to give some mathematical meat to what we've been doing, I'm going to use the same. There are a few slides here that have appeared, I guess, when we all met at UIUC last semester. I want to model these, what I call disasters, these kind of change in the system, in three possible ways. And I'm not necessarily claiming that these are all the ways, but I'm saying that at least the combination of them is a fairly large class of possible things that can happen to the system. And so the first one is a change in dynamics. So that the system, which used to be guided by x dot equals f of xu, is now driven by some other f, possibly by physical damage, for instance. The second one is partial loss of control. So whether this is kind of actively loss of control through adversarial takeover, or it is simply that some of the controllers are now under kind of environmental authority and they can just put in random inputs. But basically, I don't have the control anymore over the inputs. And the third one is actuator degradation. So the system still has the same dynamics. I still have control of the actuators. It is just that the actuators lost their capabilities somewhat. They are now capable of doing less than they used to. And so combining these three stories, we get a new kind of partially known transition model, and that's x dot equals f hat of xub, where f hat are these new, perhaps unknown or partially known system dynamics. U is decomposed into new u and v, where u is still under my authority and v is inputs that are not under the controller's authority anymore. And this uv now lives in some u hat. And u hat is the degraded set of possible control inputs. So the idea is that u hat is smaller than u in some sense. And so I want to go through these maybe from right to left, just to give a few slides on each and kind of say what we're thinking and what I think the crucial mathematical ideas here are. And so just for today, I'm going to be talking about nonlinear, continuous time, deterministic, well, sort of deterministic systems. That doesn't mean that all of these ideas that we're pushing don't apply to other frameworks. It is just that this was kind of what we started with, and it seems kind of mathematically very elegant. Yet the same high level ideas can fly in other frameworks as well. So let me start from the right, and this is a subject of my work, Hamza El-Kabir, and a few undergrad students and some of his collaborators on actuator degradation. So in this setup, we have x dot equals f of xu. And u is still under my authority, yet I don't have the same capabilities anymore. And so an example of that is this. So I found this on a sailing forum because it's a very nice picture. Where basically one of the sailboat owners said, well, there's some jam, some damage to the back of the sailboat, and so the rudder was kind of bent backwards, and so I can't move I can't move to the right anymore, or almost at all to the right. I can still make a left turn, and so he can still control the sailboat. He just has less of an interval, or less of a set that he can put in. And so now this is, of course, equivalent to, or not actually equivalent, it is less general, perhaps, to a different framework, which we just established and kind of played with in a paper this year, or last year, which is x dot equals f of x, p of u, where u lies in the original u. And p is some sort of a possibly saturation, which will reduce this set of control inputs. But it doesn't have to be saturation. It could be something that basically attenuates the gain or the size of the control input. It could be some nonlinear function that kind of changes the control input. And so what we're interested in here is, okay, I have this new system. How do I figure out what is possible about that system? What tasks we can complete? And so within the context of this talk, although we are possibly interested, or definitely interested, in more complex objectives, I'm primarily going to focus on reachability analysis. And so the question here is, okay, I have this system. This system is fully known even, and maybe I don't know something about P, but I might have some bounds on P, some under approximation of the capabilities, whatever it is. Figure out what's reachable by this system. In theory, this is not a new problem, or not even an interesting problem, perhaps, because I have fully known dynamics. And so all I'm asking you to do here is compute the reachable set of this system. Well, the system is kind of ugly, but still I know the dynamics. What can I do here? Well, the problem is that I want to do this from my kind of perspective of motivation. I want to do this in real time, or near real time. In practice, reachable sets of nonlinear systems are not computable in real time. Certainly, even meaningful under approximations of those systems, and I'm interested in under approximations because I want to be conservative, are difficult. And so what is often done in practice is computing something called the operational envelope. And an operational envelope is a kind of a proxy for a reachable set, let's say, where we say, okay, if the system is within this set, then it can do something. And so it's somehow related to this reachable set. But the point is, this computation, this description of the operational envelope takes months to develop, whether through simulations, through mathematical analysis, through extensive testing, whatever it is. So this is not something that's done in real time. Yet I need to adapt, if we want to use the word, or I need to react to an adverse event in real time. And it's impossible for me to simulate all possible adverse events and have a giant database of all possible reachable sets. And so what can I do? Well, I'm not really starting from scratch. And I think this is kind of the key idea in this chapter. I already know the reachable set for the nominal system. I know it because it was computed, or at least its proxy was computed upon system design. So I have it from before. And I know something about the degradation of the system. Somehow the degradation of the system, or of the control inputs, should tell me something about the degradation of the reachable set. So our computation of the degraded reachable set should not start from scratch. And so I'll just go through the next few slides very briefly. Basically, the idea is that, hey, if you have an old available control signal and you have a new still available control signal, what I call degraded control signal, if they differ by no more than epsilon, then certainly the hope is that the states that these two control inputs can reach also differ by no more than some h of epsilon, or whatever we want to call it, that there's some sort of a continuity argument. And this is true. There is a continuity argument. This looks like some version of Gronwall's lemma for folks who do kind of nonlinear and linear dynamics, but we can actually do better. And this is something that a student of mine has proved, where he said, okay, I can give you a bound on, given how far the available and the degraded control signal are, I'll give you a bound on how different the states reached by these two control signals are. And this bound certainly depends on what I call wildness of the system dynamics. So if the dynamics are very wild, then even a small change in the control signal can lead to a large change in the reachable or in the reached state. This is a generalization of something called the Bihari inequality, and the proof is kind of similar to Gronwall's lemma. Again, the important part is that the result depends on this wildness of the system dynamics. And so the idea is this: if my old reachable set is gray, then my theory that we developed here says that within a ball, from each gray point, and in this case my balls are rectangles just because it turns out that it's perhaps better in some cases to do things for every coordinate separately instead of for all of them together. But that within each ball around a gray state, there exists a state reachable by the degraded system, and those I denoted in red. So around in each ball around the gray state, there exists a red state. So to each gray state, I can assign a nearby red state. Now, this still doesn't exactly tell me what the reachable set is, because I can assign the same red state to possibly a bunch of gray states. So how do I know that this red set, the degraded reachable set, doesn't kind of have a lot of holes in it in some sense? It turns out it does. And that's kind of the second result, which is that any state in the boundary of the red set also maps to a nearby state on the boundary of the gray set. And so not only is red kind of a subset of gray, but their boundaries are not too far away from each other. And this gives us the recipe for how to under-approximate a reachable set of this degraded system. And we did some experiments on it. These were kind of initial experiments motivated by this ship story on dynamics that are very simple, which show that my inner approximation of the guaranteed, inner approximation of the reachable set is in green, and then the true reachable set after the degradation is in orange or red or whatever that is. Of course, I can't compute it exactly because I'm being conservative. Yet I'm getting something that's roughly of the same size. And what we're interested in now is kind of two directions. One direction is how do I make sure that the quality of this approximation doesn't diminish over time, which it currently does because of these kind of differences in the wildness of system dynamics that kind of compound. And the other question that we're trying to deal with is, okay, how do I do this for more complicated systems? And so right now we're interested in approximating dynamical systems with polynomial approximations. But certainly as kind of this initial proof of concept, we have a picture of a boat that's going from left to top right corner, and it originally has a control law that avoids this unsafe blue region. At some point, the boat suffers from degradation of the control inputs. We compute an under approximation of the degraded reachable set, and we see that this under approximation still has an element kind of to the right that doesn't intersect the unsafe set. And so we know that there exists a control law, although we still don't know what control law that is, and I'll get back to that. But we know that there exists a control law that allows us to escape from this unsafe set, or not to reach this unsafe set. Okay, so this was the first and supposedly the easiest part, which is the actuator degradation, which it turns out it's not easy at all. But a second story that I want to talk about, which is similar in some way, but requires completely different mathematical expertise, is the story of partial loss of control. And so to do that, I think I have another video.
Left to right, the stealth F-117, ladies and gentlemen.
And so if you looked at the, especially the slow motion video, kind of looking at this, looking at the F-117, you can see that a few, maybe a few seconds or whatever it is, before a part of the airplane kind of breaks loose, there is this oscillation in the lower right corner, and that's an elevon. So that's a control surface of this F-117. And at least at the very beginning, the control inputs, so this elevon is supposed to move because it's a control surface, this is its job. And at least at first, it kind of moves within its allowed range. It is clearly not moving according to the pilot's wishes, and the pilot seems to be unable to kind of counteract this motion. And over time, of course, this leads to the crash. The pilot also survived. By the way, this was an old and very famous accident, I think in '96 or something like that. And then I think that the cause was basically a mechanical fault. There were some sort of loose bolts that basically allowed the elevon to randomly move. And so there was no active hostile influence, but certainly the environment acted as a hostile actor in this case. And this is exactly what I'm trying to get at here. So I have x dot equals f of x uv, where v is now an uncontrolled system input. One of the original system inputs, or more of the original system inputs. What I want to emphasize is it is not a disturbance. It is not a small input. It's not wind. It's something that acts within its entire original authority in some sense. And so we have a two-player game here. We have player one, which is the original controller, and player one wishes to reach a state or complete a task more generally. Player two is the environment or adversary, and player two wishes to obstruct player one from reaching that state. And so the question that I'm asking here is, can player one win, regardless of what player two does? Can player one win for any starting state, for any reaching state? Can player one win if there's a time limit in which to reach that state? And there are perhaps two key features of math that I want to introduce here. One is just from intuition. I kind of said the pilot seems to be unable to counteract the bad inputs, the adversarial inputs. And so intuitively, player one wins if it can cancel out this adversarial input and still have a little bit of useful control. So still successfully kind of fight what I call the drift, or exploit the drift at the same time. And so it turns out that in linear systems or in linear unbounded systems, that's very difficult to do. But in bounded state spaces, bounded sets of states to reach and so on, fighting the drift might be possible. And in all cases, this intuition of the available input needs to be stronger in some sense than the adversary is important. And so let me try to formalize that just for basic linear systems. So if the original system dynamics are x dot equals ax plus b bar u bar, after a loss of authority over some actuators, I have x dot equals ax plus bu plus cb, where this original set of inputs or their effects, b bar, is now separated into b and c. C is no longer under my control. Then available input being stronger than the adversary turns out to be almost the same as this weird expression, which says that 0 is in the interior of this intersection. And let's unpack that a little bit. So it says that for every v, so for every bad control input, every adversary's control input, I have my own control input, u, such that bu plus cv is 0. So such that bu cancels out cv. And then I have this interior, which is exactly what I was talking about. So not only can I cancel out, but I have a little bit of, I still have a little bit of available control authority. And so let's say that now I can answer the question of how, of whether the system is resilient or not. Then the next question I want to ask is how resilient the system is. And I'll just go through that very quickly because I think it's the definition that's kind of interesting. So if the target state is in the guaranteed reachable set, or it's in the reachable set of the initial state, then by my current definition, the system is resilient. However, let's say it originally took me 5 minutes to reach a particular state, and now it takes me 4 hours. Okay, fine, it's still resilient. It's definitely not very resilient. I might get into all kinds of trouble, fuel, whatever it is. And so what I'm interested in is quantifying how much performance I lose by losing an actuator, or by losing control over an actuator. And so the idea here is to compare the quotient of the nominal time optimal reach time and the worst case time optimal reach time with the adversarial input. So the bottom here is this worst case, and of course you could argue that I could have had inf sup or max min max, whatever it is. The way that we phrased it is basically the adversary chooses an input such that whatever the controller chooses, even if the controller fully knows the adversary's input, reach time will be as large as possible. And what's cool here is that this RQ, this resilience quotient, is a number between 0 and 1. 0 means that there's no resilience. It means that if I lose control over an actuator, I'm not able to reach my state anymore. It being 1 means I have perfect resilience. I didn't really lose out on any performance by losing a particular actuator. And so we're interested in computing this RQ. But computing RQ should strike you as fairly difficult, right? This is a fraction of, at the top we have an optimal control problem. At the bottom we have an optimal control problem that's nested into an optimization problem. And then I still might want to optimize over all possible reach states or all possible initial states or whatever it is. And so these are 3 or 4 partially nested optimal control problems. This is hard. This is hard to solve, right? It turns out it is possible for simple systems. It's possible for kind of driftless systems, integrators. Optimal control there turns out to be optimization. Optimal control inputs can be geometrically determined. There's this notion of direction in which the adversary is the strongest, and it's possible to determine the least resilient goal state. And this is something that a student of mine who recently graduated called the minimax maximax quotient theorem. This already is not easy. So he published a paper in the Journal of Optimization Theory, and the paper is 15 pages or so, and it's basically just the one proof of this theory. So, and this is just for driftless systems, right? I'm not even talking about fully nonlinear systems. I'm talking about kind of these toy examples. So the question that we can ask, okay, well, how do I go from this into the real world? How do I start talking about real linear systems, even nonlinear systems? It turns out that even for general linear systems, this is not possible to analytically determine, or the optimal control signal is not possible to analytically determine. We just know that it's bang from the Pontryagin minimum principle. And so what we do here is we try to bound this resilience quotient. We say, okay, I'm going to look at the lower bound of the nominal optimal reach time through a bound on the flow of a Lyapunov function. I'm going to look at an upper bound of the nominal optimal reach time, lower bound of the worst case optimal reach time, upper bound of the worst case optimal reach time. And so now this is going to give me some sort of bounds on this resilience quotient. So if I know that the resilience quotient is at least 0.5, that says, okay, well, at most, if you play perfectly, you will lose half of the, or you will lose double the time, or it will take you double the time to complete your mission. But this is still for linear systems, and so already here we kind of start to feel our theory slipping. And so what do we do for nonlinear systems? And so we started playing with that now, especially kind of within the context of this ULI project. And what the current feeling is that so time resilience is hard. And that's because even simple looking optimal control problems in terms of minimal time are actually not simple. So determining the minimal time to reach a target just for nominal dynamics with input constraints is not a simple problem. Yet determining minimal energy to reach a target for nominal dynamics is a simple problem. It has something to do with the controllability gradient, at least for linear systems. And so what we're currently kind of hoping, or we're getting some initial results, is that perhaps by moving from this notion of quantifying the time resilience, if we move to the notion of quantifying energy resilience, that will get us one step further. That will give us some pathway towards nonlinear systems, saying something along the lines of, okay, well, if the system is nonlinear, how much more energy do I lose compared to a linear system that's close to that? And so one possible idea here is to describe nonlinear system using some sort of Koopman methods as a higher dimensional linear system, and try to perform these kind of energy resilience calculations on that. And so we've gotten some initial results. A student of mine is hoping to submit actually a few papers on this topic within a few months. However, going back to the work that we've kind of completed, that we have some results. The first thing that we kind of played with was, okay, well, since I had that video of F-117, we took a model of a fighter jet, not F-117, but an academic fighter jet called the Admire model. And we said, okay, well, if you lose the right elevon, are you resilient? Or in other words, could the pilot have done something better than what happened to that airplane if the environment was as mean as possible, if the environment was kind of playing exactly the worst things for the pilot? And it turns out that this is a question ultimately of finding some eigenvalues or minimal eigenvalue of some matrix. And it turns out that the system is indeed not resilient. So if the environment played exactly the worst, there is nothing the pilot could do to keep the system stable or to reach this kind of stability state. We've started playing with this in some other applications. So we have this notion of time delays that I'll still spend a minute on with satellite inspection, and so we're kind of pushing that forward. Let me not go into that further. Let me go into the third possible kind of class of disasters that I promised I would be talking about, which is mostly the hardest because it kind of it subsumes the previous two classes, and that's change in dynamics. So in this case, instead of x dot equals f of xu, I now have x dot equals f question mark of xu. And this question mark is an unknown function. This is not a disturbance, and this is not finitely many unknown parameters. Importantly, because of this, so all the great methods that we have of robust control or classical adaptive control kind of focus on the original target remaining reachable, but the original target might not remain reachable, and to do that, I have kind of a video. So these were RC airplanes, but certainly the airplane that's currently in pretty much free fall, there's no God of robust control that's going to make you proceed with your task, right? And so the question here is, okay, what can we do? What is there a reasonable destination? Is there a reasonable outcome that allows me to, salvage whatever I can from this mission? And so the question that I'm interested in is, what is the system certifiably capable of doing, even if I don't yet know how to do it? And the answer is, well, it depends on what you know about the system. If you don't know literally anything, if the dynamics can just change randomly at any given time, and there's no rule to this, it can kind of jump around entirely, and you have no knowledge of it, then, yeah, you can't prove anything. Nothing is certain, right? However, if you do have some class of possible ground truths, and I'm being very broad here, this doesn't need to be a small class, it can be an infinite class, it can be unbounded, whatever it is, I can define this notion of a guaranteed reachable set. And a guaranteed reachable set is just an intersection of all the possible reachable sets. So intersection of all the reachable sets for all the dynamics that are consistent with the current knowledge. And so I know that if I'm in this guaranteed reachable set, it means I'm reachable by all the possible ground truths that I haven't disproved yet. Okay, so I defined this guaranteed reachable set. What do I do with it, right? How do I compute it? If you look at it, I'm asking you to compute an infinite intersection of reachable sets of, so infinite and weirdly parameterized or not parameterized, intersection of reachable sets of nonlinear systems. How do I do this? How do I do this in anything close to real time? And so the idea here is, let me try to figure out all the velocities in which the system can move, all the what I call guaranteed velocities, which are all the velocities that are available for all the possible ground truths at time t. Okay, how do I find the guaranteed velocities at time t? Well, kind of intuition says, well, if you can figure out where you can move right now, so at time 0, and you have some bounds on this maximum system wildness, then you can start talking about how to what you can guarantee at time t. Okay, so to do that, we need these two pieces. What are the velocities guaranteed at time 0, and what is the maximal system wildness? So the first one can be computed ideally in an arbitrarily short time, although that kind of depends on your system response and the resolution by which you can kind of change your controls. But basically, by kind of this notion of persistent actuation, you can compute the set of initially available velocities. You can get a bound on the change in the set of the available velocities from known system parameters, possible Lipschitz bounds from physical laws and or design knowledge. So it turns out that we can compute these guaranteed velocities, still not easily. These are, again, infinite intersections of now perhaps geometrically more simple objects, at least than the reachable sets. How do we under approximate those? Well, an initial idea is, or the idea is, fit some sort of a simple geometric object within this weird intersection. And so our initial idea was fit a maximal ball, but then there's better ideas. Fit a polytope, fit an ellipsoid, fit whatever it is that you can then perform, that you can then kind of try to find reachable sets of an ordinary differential equation or inclusion that's kind of generated by these sets. So we've done this. We computed some guaranteed reachable sets. Turns out that this is a so computing a guaranteed reachable set using our method is computing a reachable set of a what I call quote unquote simple control system. We've done this again. An issue is, first of all, we've done this for simple systems, and the quality of these guarantees falls over time. So we can provide meaningful guarantees only for short times. And importantly, what I said I would get back to, I didn't really speak anything about control yet, right? I just said, okay, I will have some ideas of establishing what the system is capable of doing. Yet I don't know yet how to do it. And so what we ultimately want to do, and I mean what we, if I can even speak for the entire project, what the idea of the project is, we want to have this kind of end-to-end planning, learning, and control. So we want to figure out what tasks can be provably completed. So I call that task assignment. We then need to know what we need to figure out in order to be able to complete it. So we need to have some sort of learning or real-time learning, whether we want to call it learning or adaptation or figuring out how to be robust, but we need to have some sort of a real-time estimation. And so our method of doing that for now is this persistent excitation, but it's not necessarily the only method. And then we need to perform, in as much as possible, assured control. So once we figured out the task that is to be completed, we want to complete this task. And so we've started playing with the learning part of it. We've started playing with assured control for simple, for kind of simple tasks. Hey, just follow a straight trajectory. Just reach a particular state that you're guaranteed to be able to reach. We can do better, and I'm saying in particular in terms of the ULI project, we can combining our work with the work of others, we can get further than these simple examples. Okay, so now I've hopefully kind of convinced you of mathematical interests and that we have a clue at how to attack all three of these problems. And so what I want to spend maybe the last 5 minutes on is saying, okay, what's next? What do we still need to do? The way I see it, we have two major challenges. The first one is complexity. I don't necessarily just mean computational complexity. I mean, what are the systems for which we can estimate these capabilities? What are the capabilities that we can estimate? So right now, I'm just talking about reachable sets. Can I talk about some more interesting, some more complicated the control specifications? And then the second one is what I call validation. And I don't necessarily just mean formal validation, although that's certainly a part of it, but in reality, what can we do on board during or immediately after a disaster, after an adverse event? And so just some thoughts on our efforts to proceed in both of these lines of interest. Complexity is kind of, I feel, a lower hanging fruit in the sense that at least we know what we don't know. So a lot remains to be done. We have a lot of technical assumptions. Linear systems for loss of control authority for now, kind of full actuation for unknown dynamics. These kind of annoying yet important technical assumptions. We also want to combine these scenarios that I was talking about, and we started doing that. Importantly, we can start being smarter. We can talk about structural knowledge of the unchanged part of the unknown dynamics. We can start talking not just about reachability, but about safe reachability. And then we need to start building a richer mathematical theory here. We need to start talking about time-delayed systems. We need to start talking about systems operating under state constraints. And so we started doing that. We've done some initial work on time-delayed systems, in which case, if there's an adversary playing against you and you are delayed by time, you don't have a perfect response to the adversary. And so reachability is unlikely, yet approximate reachability might be attainable. And so we can ask, okay, how much damage can the adversary do by exploiting delay? How imperfect can I be if there's a delay? Intuitively, that depends on how large the delay is and how wild the system dynamics are. And so the results that we have on this kind of amount of imperfection or loss of performance by the delay turns out to exactly depend on how strong the adversary is, how wild the dynamics are, and how large the delay is. A second kind of teaser that we are just going to submit a paper on this, and this is really really exciting, I think, from a mathematical point of view. We're interested in these state constraints, and so what we're interested in is developing a guaranteed reachability theory on subsets of Rn or on manifolds to be specific. Now, if I'm operating on a manifold, already the notion of an ODE is kind of difficult, right? Because my X is on a manifold. My X dot is then on the tangent space of a manifold. And so finding the reachable set of a known system on a manifold, and a manifold, as one of my earlier circles showed, but I kind of passed over it, a manifold is a kind of a side information. I know that the system is operating on this subset. Finding the reachable set of a known system on a manifold or on a subset of Rn is already a challenge. Analytical methods are hard enough on Euclidean spaces. We don't necessarily even know how to approximate solving ODEs on a manifold, and so there's just no good tools to do that. The ideas for guaranteed reachability at high level, they kind of remain the same. Yeah, exploit maximal wildness of the dynamics. But maximal wildness now becomes more difficult because it's no longer just Lipschitz constants. It's sure Lipschitz constants on surfaces or on manifolds, which has to do with the manifold curvature, which has to do with the Riemannian metric. So this is something really, really exciting that I think merges the kind of mathematical richness, the mathematical well, with what we really need in order to simulate or to work on real systems with state constraints. And so now I want to talk about this kind of high-level story, the long-term story of validation. So how do I actually go from little toy examples to real systems? Real systems have sensors. Real systems have perception that helps us recognize fault type and gather information, whether that's a good thing or not, because sensors and perception are imperfect and our models just currently say, oh yeah, you can see the system state immediately. It is reality. So we need to use those. We need to develop methods of fault detection, sensor fusion, and state estimation simply in order to get the state to perform this guaranteed reachability computations. This is a part of our ongoing joint work with the rest of the TC3 team, with Ali and Yanis. Importantly, though, we want to perform complex missions in high fidelity simulation. So we want to have concurrent sensing and actuation faults. We want to have hostile action, and by hostile, I mean also environmental action, plus this kind of regular noise that aircraft is used to. In order to do that, we want to make use of kind of high fidelity simulation tools for instance, Guam. In the very long term, we want to start thinking about actual onboard implementation, where my computational constraints and time constraints are much more critical. So we want to start getting some real results on what can I do with time delayed controls, and how complex are my computations, whether I can perform them in real time. So right now, a lot of the things we do are, yeah, they're better than naive ways, and we can do them perhaps on a personal computer, but can we do them in real time with the actual hardware that would be up on board? And so I want to stop here. I want to acknowledge the extensive support that we have from NASA, including the current ULI, but also some other projects, the support from the Department of Defense and the Discovery Partners Institute. I also want to point out that I'm only able to speak here because I'm a mouthpiece for so many great researchers that work with me. Hamza Al-Kabir and an undergrad previous, Anipir Osmanishvili, who did the work on actuator degradation in collaboration with Joe Bensman and with folks from JPL. Jean-Baptiste Bouvier, Kathleen Shu, and Ram Padmanabhan, who are doing work on partial loss of control in collaboration with folks from PNNL and some of our other faculty members at UIUC, and Taha Shafa and Yiming Meng, who are doing work on unknown dynamics. I'm, of course, happy to take questions, happy to chat, whether online or offline. Thank you.
Okay, Irene, go ahead.
So Melkior, thank you. I have a question. So especially for the part of the work that deals with just the degradation and control authority, right? Have you considered taking your framework and seeing how it would collapse into things that we already sort of know about that type of problem, right? So adaptive control is very good at dealing with degradation and authority of control authority, right? And there's other things that allow you to basically see what happens when you have degraded authority in terms of what can you do as something as simple as can you continue following the current trajectory to reach your destination, or maybe just a simple replan will allow you to do that, right?
Right.
Have you considered looking at collapsing it to see how they compare, because it may give you a sense of
I think that's
conservatism.
That's a great question. That's a great question. I would say that the answer is so we've done some I would say not necessarily comparisons with adaptive control, but with kind of fault tolerant control design and things like that. But what I think is particularly interesting that you mentioned and that we haven't done yet is I think that we've kind of, I guess, focused so far mostly on a problem that is complementary to control design. So we were mostly interested in figuring out what the system is definitely capable of doing, not necessarily how to do it. And how to do it is a very difficult question that we ultimately, so I wouldn't even necessarily say we want to just compare with adaptive control. We want to use it, right? We want to have this pipeline where I say, oh yeah, my simple method tells me that you can do this. Now I have no clue how to do it. Let me use some adaptive control methods to actually do it. And so this is certainly a part of kind of our integration with the other folks.
So with you on that, it's the idea of what can I do? It's at the mission level question, but my point is that if you try to simplify it to something, follow a trajectory, right? That's my mission. To see how your framework collapses to something that we know the answer to.
Okay. That's
right. So it's not even so much the how to, but adaptive control is something that allows me to follow that trajectory. It's both the what and the how, right? But in your framework, again, it's on the simpler side of the problems, perhaps. But again, to me, it's a really good check to see how it collapses, if it does, and if there's conservatism that's inherent, where is it? Right. It might give you insights into more complex systems.
I think that's a very good question that I'll this is something that I'll immediately bring up with my students. So we always kind of thought of it as two different sides of the same coin, but from what you're saying is basically, hey, we should just say, okay, let's try to see whether these are secretly kind of, whether they are secretly the same thing in some sense for at least some possible missions.
Yeah, how they collapse, right? Because there's some things where certain methodologies at the end of the day, if you go from nonlinear systems to linear systems, you recover sort of your control, for example, right? And that gives you insight into your more complex controllers. So more from that perspective.
Right. Yeah, that's, I think that's a great idea. We'll talk about that. Yeah.
Thank you.
I have a quick question. Maybe not so quick, but a couple of questions. One is, when you talked about these under approximations, you didn't specifically talk about data structures, like what is the representation of these under approximations. Does that matter in the way you're approaching the problem?
Yeah, I didn't talk about it because, so I think this is a very important question. I think it is also a question that I feel would take me kind of another hour to elaborate on completely. Certainly it does matter. And I think it matters in two ways. First of all, it clearly matters computationally what my representations are. And even in terms of just doing it. So for instance, in that first story of the actuator degradation where I said, oh yeah, I just kind of take off rectangles from the boundary of the nominal reachable set. So I need to have a representation that allows me to do that in a very simple manner. And in some parts of this work, we've gotten very good, I think, at those representations. So at least in the first part, so with the actuator degradation, the representations that we're interested in are zonotopes. And it turns out that we can do a lot with zonotopes. Sometimes we are worse at it. And so in the representations in the third part, where I just kind of compute this reachable set, and I showed you a picture, the representation is kind of a point cloud, and it is simply obtained by Monte Carlo methods, which is computationally heavy, and even in terms of memory, it's heavy. So yeah, to answer your question, it certainly does matter. This is something that we think about, and this is not something that we kind of have a final answer to, but we have some ideas of what might be better than others.
Yeah, so there is a lot of ongoing work on coming up with the right data structures for doing these computations, like generalized star sets and so forth. That might be interesting to look at. And
that's that's exactly, I think exactly the keyword that you mentioned is something that my student is right now looking at. Yeah.
Excellent. And so the related thing I was thinking about is you hinted at these problems being hard, and there's some notion of difficulty, and you also mentioned that it's not necessarily computational complexity is the measure of hardness. So in what sense are you thinking about this problem being hard? And if one solution to the problem is better in some fundamental way than another solution, how do you make that claim?
So that's a very good question. So certainly I would say, so computational complexity is a big part of the problem. Another part of the problem is that mathematically, we just don't know how to do some of the things. So this is not necessarily just a question of, hey, it's gonna take me a long time, but if I sit at a supercomputer for 2 years, it's gonna spit out the result. There are some questions that just don't necessarily have the kind of mathematical theory developed to do it. So for instance, with the computing reachable sets on a manifold. So we right now know types kind of how to define, so, or not that we know, people know how to define ODEs on a manifold. Now, how do I actually solve these ODEs on a manifold is not a question of just computational complexity. It is the question of, if I embed it, if I embed this manifold in Rn and just treat it as a part of Rn, I will always get approximation errors that will lead to the reachable set technically being outside of the manifold. So it is not kind of the computations are not aware of the constraints that exist in the system. And so it's questions like those where it is not, hey, I will be better if you give me more time, but also I need to have the tools that are aware of the system structure. And I think for a lot of these questions of, infinite intersections of things, or computing sets on manifolds, we don't have the tools and the theory that kind of are aware of this structure.
Thank you. Thank you for the taking the questions and the great talk.
Thank you so much.
More questions? If no more questions, I'll just ask one philosophical question, right?
Sure.
So this is about like estimating reachability and understanding how to do it. I mean, when you presented in the beginning the motivation, it just reminded me of our prior NSF grant on Virtual Sally when we were trying to estimate, trying to understand what worked in his brain to estimate that landing in Hudson would be safer than heading towards any of the airports. And in the result of that grant, it was jointly with Louis Shah, and Petros was also part of that grant before he left for UNR. So we came up with a paper that was recently published in AIAA. I can give a brief overview of the paper, and I can put the link here, I mean, in the chat, so you can, in case you are interested in reading it, you can download and read it. I don't know if I pasted it correctly or not. Hold on. Right here. So here is the link. So basically, the way we formulated the problem, that for commercial aviation, the safety implies having an airport within an hour of landing. That's the ETOPS rule, within an hour of landing, and then the big flight envelope kind of takes this into consideration, while going for aerial robotics platforms, in most of the cases, they all were spanned out of ground robotics, where model predictive control was the bread and butter, and the model predictive control went up into the air without consideration of this ETOPS rule from the safety perspective. And we tried to do this multi-objective optimization for calling it backup constraint model predictive path planning that would account for these type of constraints. This is a different perspective as compared to what you are doing. You are coming from the classical reachability literature, formulating the problems, going for time delay systems, all these types of things. Ours comes from that ETOPS rule on commercial aviation, and a different perspective. I just wanted kind of to share what we have done, and maybe you take a look, and maybe something comes up in the result of it as a collaboration between our groups, and that could have more impact or what. Just check the paper, I put it in the chat. It's already, I think it's already published in AIAA at the JGCD. It was accepted maybe a few months ago, but the early access should be available, but I'm not sure it already has page numbers or what, but it should be available from AIAA publication site as well. Just wanted to give you this different perspective. Not that I'm questioning what you have done, but that a different way of coming to the same problem. And the Sally grant was our inspiration on that path. And we have kind of stability proofs and other stuff as well.
Yeah, that's great. And so I was, I'm not aware of the paper that you just said was published, but we were, in fact, when I was kind of trying to find this this video that I showed at the beginning, that was inspired in part by your work on the virtual Sally. And so Sally, we have kind of a, like you said, a slightly different perspective that's kind of more in terms of classical control. But yeah, certainly at least on a high level, the stories are quite compatible. So I'm looking forward to looking at this paper.
Right, and then I have a student that I'm sure he would be also maybe happy to work in between us. Just check and see.
Yeah, for sure.
And we can have a separate offline meeting on that.
For sure.
That's all I wanted to say. And basically, I want to thank everyone for attending this first seminar of the year. And at 1 p.m., I expect to see all the co-PIs and thrust leads for the 1 p.m. meeting, because we want to do some changes, right? In few months, we'll run out of co-PIs. We can definitely go back and repeat everyone presenting their annual progress, or we can invite external speakers and take different perspective, come up with models that we would like to test, have some type of more precise plans, as we're kind of looking forward to phase 2 extension. So at 1 p.m., I hope to see many of you on the call, okay?
Perfect. Thank you all for
Thank you,
coming.
Melkior. Thank you. And hold on, how should I stop the recording before you all leave, or it automatically? Okay, I stopped the recording. I should get the video. Melkior, please send your slides, okay?
I will do that. Sounds good.
Thanks.